Hello everyone, welcome to the first of many videos on your final study guide for second semester. Year is 2017. So let's talk a little bit about the stuff that I want you guys to bring on the day of your final. So this final study guide is not optional, it is mandatory. It's the last assignment for the year, so it's worth points. I also am allowing you guys to bring in one 3x5 card. You can use the front and the back, which is really generous. You're going to want to bring a scientific calculator because I can't guarantee that we're going to have enough to share, and a number 2 pencil. So one of the things that I also recommend is that you bring your planner just in case you have to use the restroom. Nobody brings planners on the week of the final, but then they have to use the bathroom and then have to write passes. It's really not a big deal, but just saying. All right, on the class website, I want to show you something. So flipping over here. Okay. We have some old videos from last year that I have collected, and they're not good or bad, it's just that we taught different content last year. So you're going to see some videos that have some questions on there that you don't see on your final study guide. But the question style is the same, maybe some of the numbers are switched up a little bit, but basically it's the same content, and so they're still good, but obviously I'm going to be recreating those videos slowly as we go through. Anyway, another thing is you'll notice on number 2, this is very cool, we actually have a list of the answers. Now I need to make sure you understand that this is last year's study guide, not this year's. So all it does is it lists what the answers are so that you can check yourself for confidence. Okay? So obviously I'm going to be recreating that, and I'll let you know once it's updated. You'll probably see after that, the year 2017 after that. It'll say key 2017, and you know that that's the most recent one. All right, you'll notice also that there's a Jeopardy game posted. The Jeopardy game is, again, from last year. We had enough time to do Jeopardy last year, and it was kind of fun. And it has just really good review questions, old stuff like moles and molar mass, and maybe a little bit of acids and naming and formula writing. But anyway, if you keep going on the class website, you'll notice that I posted some helpful videos. We've got reminders on how to do conversions, how to find, mass to moles, moles to mass, some stoichiometry basics going from particles to moles to volume, and then limiting reagent problems. And then if you keep going, we also have that oxidation reduction that's going to be on your written portion of your test. You're going to have a written and a multiple choice portion. Some of the other chemistry teachers, they didn't quite go into the same depth that I did on oxidation reduction, so that's going to be on the written portion of your guys' exam. And then we also have some pH and POH and acids and stuff. Okay, so use the website. You'll notice when you come to the honors chemistry and you start looking at all of the units, if you click on it and it doesn't load the page, that is because that content is not taught in second semester. So I only have the web pages active for the content that is actually on your final, okay? Don't forget that in the reactions unit, we also covered stoichiometry. So that's actually basically kind of like two units in one, okay? All right, well, shall we begin? Separate sheet of paper, calculator, and all that good stuff. Let's roll. Starting with, number 1. It says, what is the molar mass of calcium chloride dihydrate? All right, so let's begin. Number 1, calcium chloride. So calcium on the periodic table is Ca. You're making a hydrated salt. Hydrated salts are ionic, and then they have water molecules attached. You guys kind of remember that? All right, good. So calcium has a positive 2 charge. Chloride, that's Cl, he has a negative 1 charge. So when you slam those two together, always make sure you're writing the cation first, the anion second. And so this will be CaCl2, good job. And what does dihydrate mean? Yeah, you still have to remember all of your prefixes. Do you guys still remember those? That might be something that you might want to write down on your flashcard. You guys get to have a note card. You may want to just kind of refresh your memory on those prefixes. How's it go? Mono, di, tri, tetra, penta, hexa, hepta, and then octa, nona, and then deca. All right, those are the ones you're expected to remember. So this is dihydrate. That means that there's 2. So there's 2 waters. How do we attach it? What symbol do we place between this compound and the water? You guys remember that little dot thing? Yeah? And then a coefficient of 2, and then your H2O. All right, so there's your formula, number 1. It says, what is the percent by mass of water in the previous question? Okay, so question number 2 wants, oh, by the way, don't stick charges on your formulas. You guys remember I always get kind of picky about that. Does it ask about the molar mass of number 1? Oh, sorry about that, guys. All right, so let's go ahead and do the molar mass. And by the way, you kind of have to have the molar mass in order to answer number 2 anyway. All right, so let's get the molar mass of this bad boy. All right, let's go. Calcium, periodic table. Make sure you check that molar mass because a lot of people just say 40.0. It's not 40.0. What is it for calcium? Yeah, it's 40.1. Chlorine, another very common element that gets mixed up. What's the molar mass for chlorine? 35.5. Good job, guys. Got to round it, okay? And then you just double this bad boy. Okay, so this is your calcium chloride side. And then water is super easy. I kind of have it memorized. And this is 18.0, but then you see how you have 2 of them? What do I do to this value? Times that by 2. All right, so let's get both of those quantities and just see what they are, and then we'll add them together. And plus 2. Okay, I get a grand total of 147.1. So check both sides and just make sure you're doing it right because we're going to need this information in just a second. On the left, the calcium chloride piece is 111.1 grams. And then on the right, the 2 waters is 36.0 grams. All right, so water comprises 36.0, calcium chloride is 111.1, and when you add those together, you get a grand total of 147.1, and this is grams per mole, molar mass. Right on, right on. Okay, number 2 wants you to do the percent composition for just the water, right? So how do you do percent composition? Do you guys remember that? So it's always part over the whole. Do you guys remember me telling you that? It's always part over the whole. So the small number on top, the grand total on the bottom. So water comprises 36.0 of those grams. So we're going to put the 36.0 grams on the top. We're going to put the 147.1 grams on the bottom. Hey guys, mental check. Why don't I put just 18 on the top? Yeah, right, because there was 2 of those waters. All right, let's divide 147.1. All right, I get approximately 24 point, if you round it correctly, 0.5%. So 24.5% of that compound is made of water. Okay, let's go back. All right, so we got the percent of water. So it says number 3, if the hydrate in the first problem is dehydrated, what mass of anhydrous salt should remain? So I didn't give you guys a mass. That's kind of unfortunate. I think what I meant to do is say if the hydrate in the first problem, how about if you have, let's change this. If you have, I don't know, let's go with 4.89 grams of the hydrate in the first problem, what is the mass of the anhydrous salt that should remain? Okay, I'm making that official change. I'll totally update that on the class website for you guys. Just stick this on the desktop real quick. Okay. All right, so now they're telling you in problem number 3, they're telling you that you have 4.89 grams of this stuff. So you have 4.89 grams of the calcium chloride dihydrate. And they are asking you basically to heat this sucker up, to dehydrate it, to get rid of the water, and they want to know what mass will remain. Okay? That's why it is super awesome that we've already done kind of like this percent for water. That is the percent of mass that you should lose, right? Because that's a percent of water. So how do we figure out what 24.5% of this mass is? Do you remember how percents basically work? It's always part over the whole, and then it, you know, times 100, and that equals your percentage. So if you want to, you can say, all right, I should be losing 24.5% of this chunk. We want to know what part of that is 24.5%. So we know that the grand total mass, or the total, which is the whole, which goes on the denominator, is 4.89 grams. We just don't know what part of that is 24.5%. And then, you know, if you want to, you can say times 100. Okay, so you see this times 100? The first thing I'm going to do is I'm going to divide all of this stuff by 100 to get rid of that times 100, and basically just changing that percent into a decimal form. So 0.245 is equal to x over 4.89. All right, so now it's pretty easy to solve. I'm going to take the 0.245 and multiply it by 4.89. Now remember, this is going to represent the mass that should be lost. This is the mass of water that is in your hydrated salt. So the mass of H2O that is in your hydrate is 1.19805. Hey guys, what do you think we should do about our sig figs right now? Carry it, look, see, probably 3. 1, 2, 3. The last value is that 9. Does the 9 need to be rounded up? The 9 is going to turn into a 10 then, and so basically this turns into 1.20 grams of water is in your hydrate. So this does not represent how much should remain. This represents how much should be lost. So let's take that 4.89 grams. This was the original mass, remember? And we are going to subtract 1.20 grams because that's how much water we had. So you get 3.69 grams of dehydrated salt should remain. Okay. Okay, does number 3 make sense? Any questions so far? All right, excellent. Let's keep going then. All right, number 4. What is the formula for magnesium sulfate heptahydrate, and what is its molar mass? So the reason why I'm doing this one is because this is Epsom salts. You guys remember that lab that we did? This is the salt that one of the salts that we were using. All right, so number 4. Again, it's called magnesium sulfate. And sulfate, 8s and ites are on your list. Sulfate is SO4, and you can check your charges. Magnesium, element 12, is going to be a positive 2. Sulfate, you can look it up, is a negative 2. So these guys are like a perfect match. So just MgSO4. Now, the last part of that, look at the last part of the name. Heptahydrate. Do you remember what hepta is? Hepta, right there. That is 7. So we're going to be attaching 7 waters to this guy. So with a little dot, 7H2O. Okay, now I think number 4 is asking you for what is its molar mass. Okay, so we've got the formula. Now let's get the molar mass. So this is just good practice, okay? We've got magnesium, sulfur, oxygen, and then over here water is technically, if you just have it memorized, is 18.0 grams. And you have 7 of them. All right, so let's just break it down and see what we get. Magnesium is 24.3. Sulfur is 32.1. And oxygen is 16.0, but you've got 4 of them. Let's see what you get. Okay, I'm just doing all of this in one step. The grand total is 246.4 grams. Can anyone actually confirm that? Sweet, thank you. So 246.4 grams per mole. Okay, number 5. What is the empirical formula for a compound that has 8.65 grams of iron? Let me copy that down. Let me make sure I got it right. 8.65 grams of iron. And 3.72 grams of oxygen. 3.72 grams of oxygen. And they want to know, let me just double check the question, they want to know the empirical formula. So the empirical formula is the formula that just basically represents the lowest common ratio between the two elements. So I remember we did kind of percent to empirical formula, but what do you do if you've got mass and you have to go to empirical formula? Yeah, you could start with the percent composition. That's a great way to go about it. But there's actually something that you can do that's much easier. You can be given percent and change a percent directly to mass. But if you've got mass already, guess what you get to do now? You've got mass. Just convert it to moles. You get to jump right into that step. Okay? So let's go ahead and do the 8.65 grams of iron and convert that to moles. And take your 3.72 grams of oxygen and convert that to moles. All right, let's see. Iron is 55.8. And oxygen is 16.0. So is this bringing back some memories, guys, of stuff that you learned? It's always good to review. You guys are going to get so tired of reviewing. You're going to be like reviewing in all of your classes. Notice I'm reducing to the proper number of sig figs here. And why did I do just oxygen and not O2? Yeah, it's the element. Good job. It's the element. We're looking at how many elements we basically have in the compound. Okay, not how many oxygen molecules we have in the compound. All right, so this represents how many moles of iron I've got, and this represents how many moles of oxygen I've got. So those don't look like pretty numbers. I can't really tell what the ratio is. Not quite, not yet. So what do you recommend is the next step? It's been a long time since you've done this. Right, good job. We have to reduce. We have to somehow get whole numbers. And so the best way to do that is to divide both of these values by the smallest value you've got. Smallest value you got is 0.155. So let's take both of these and divide by 0.155. And let's see what we get. This will obviously be 1, but let's check that other one. And I get approximately, I mean it's pretty darn close, 1.50, right? And this is exactly like 1, obviously. So if you're watching your sig figs here. Okay, so 1.5 is not a very happy quantity, is it? We're looking for whole numbers. So if you ever see a 1.5, you know you've got an issue. What do you think we should do there? Yeah, we can actually just multiply by 2, or you can divide by 0.5. Either way, it's the same. It's going to come out the same. So I'm going to take these guys and I'm going to do whatever I do to one, I have to do the other, so it's equivalent. So this is going to become a 2, and this guy right here is going to become like a perfect 3. So how many irons do we have? We have 2, so this is your formula, okay? Fe2 and O how many? 3. There you go. That's your empirical formula. Is there any way I could ever reduce that formula anymore? A 2 to 3 ratio does not reduce. You're done. Okay? Alrighty, so now we're on number 6. It says determine the solubility of the following. So we have 6 A, B, C, D, E. So you may just want to kind of jot those all in, and then we'll just do all of them, okay? So number 6, A, B, C, D, and E. Okay. All right, so I've got some solubility rules kind of hanging out right here, so we'll check those out, okay? Here we go. First one is silver nitrate. So if you're looking at your solubility rules, you're looking for the rule for nitrates. It's right here on the top, underneath water soluble, but let's read it all the way through. All nitrates, chlorates, and acetates are soluble, and you notice that they don't list any exceptions. Some of these have some exceptions, but nitrates and chlorates and acetates, they don't. So on number 6, part A, silver nitrate is soluble. So do you guys remember how we label soluble substances? What's the symbol for soluble? AQ. There you go. You can go like this or just say yes. That's also acceptable, okay? So aqueous or yes. All right, let's go to the next one. Calcium sulfate. All right, so let's pull out the rule for sulfates. Right here at the very end of your soluble substances, it says All sulfates are soluble except calcium, strontium, barium, and all of those. So which sulfate do we have? You have calcium. Isn't calcium one of the exceptions? It says it right there. So it says all sulfates are soluble except calcium. So unfortunately, we can't label this as soluble because it's one of the exceptions. So on this one, how do we label something that is insoluble? What's the symbol? S for solid, and then if you want to, you can say no. Okay. Part C. Aluminum hydroxides. We're going to look for the rule for hydroxides. It's down at the bottom. It says all hydroxides are insoluble, except those of alkali metals, calcium, strontium, and barium. So the question is whether or not aluminum is an alkali metal. So on your periodic table, let's grab that. All right, so your alkali metals on the periodic table are all the way on the far left-hand side underneath the hydrogen. Aluminum is not part of this group, right? So you do not have something that is soluble. You have aluminum hydroxide. Hydroxides are insoluble unless you have an alkali metal. You don't. So this should be labeled as insoluble. So I would label this as an S and just say no. All right, let's keep going. Oops, wrong tab. Let's see, part D, magnesium phosphate. Magnesium phosphate. So let's find the rules for phosphates. Right here, underneath insoluble. So it says all of these, phosphates, blah, 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 are insoluble except those of alkali metals. So you have to kind of go back and see, all right, what metal did they have in front of that phosphate? They had magnesium. So check the placement of magnesium. Magnesium is in the second family. Is that an alkali metal? No, it is not. So come back over here. Let's double check. It says phosphates are insoluble unless you have an alkali metal or ammonium, and you do not have either of those. So this one should be labeled as insoluble. No. All right, next one. Let's do potassium carbonate. Ooh, potassium. Let's talk about where potassium is on the periodic table. Do you guys see him sitting right there underneath sodium, right there? Potassium is an alkali metal. So anytime you see an alkali metal, I don't know if you noticed this, but on the solubility rules, it always says that anything that's an alkali metal is always soluble. In fact, if you look at kind of up here at the top, the very top part, it says all sodium, potassium, and ammonium salts are always soluble. No exceptions. So if you forgot that, and maybe you kept kind of hunting and you went down to the last name, carbonate. So let's look at carbonates and what it says. It says all carbonates, blah, 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 are insoluble except, dun, 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 alkali metals. So this guy is soluble through and through. So we would say AQ or yes, whatever you prefer. Okay, let's go to number 7. What symbol do you use for aqueous? AQ. And precipitate? Solid. S. All right, number 8. How many moles of carbon dioxide? Hold on. How many moles of carbon dioxide? Can you cross off that word 1? That's stupid. How many moles of carbon dioxide would there be in 15.26 grams of it? All right, so we're starting to go into mole conversions. 15.26 grams. 15.26 grams, and this is carbon dioxide. And what do they want you to convert to? Moles. All right, so this is a nice simple one. We're just going to go from mass to moles. All right, in order to go from mass to moles or moles to mass, you need molar mass. All right, so carbon is 12.0 grams per mole. Oxygen is 16.0 grams per mole, but you've got 2 of them in the formula. All right, let's hook that up. I get 44 grams per mole. All right, so 44.0 technically grams per mole. So when we set up the conversion, you have one rule. Follow the unit so that you can cross-cancel. So if you have grams sitting on the top, you have to have grams sitting on the bottom to get rid of those grams. Look at your molar mass. So how many grams should I put down there? 44, technically 0.0, so we can watch our sig figs, right? And that's per 1 mole. This will cross-cancel grams. 15.26 divided by 44.0. Let me tell you exactly what I get on my calculator so we can just quickly review those sig figs again. This first value that was given to you in the problem has 1, 2, 3, 4 sig figs. This guy has, you know the two 4s are good. But what about the 0 at the end of the number? Yes, zeros at the end of the number are only significant if they appear after a decimal. Remember, they have to be at the end and after a decimal. Okay? So this is 3 sig figs all around, 1, 2, 3. Just check the last one. Do you need to round that 6 up? Yeah, so this should actually be reported as 0.347, and you converted to moles. That was the only unit that did not get cross-canceled. So that's how many moles of carbon dioxide you've got. Okay, that was number 7. No, that wasn't. That was number 8. My bad. Number 7 was just too easy. All right, then let's move on. Number 9. How many milliliters at STP? What does that stand for? Standard temperature and pressure. What is standard temperature? Let's recap. 0 degrees Celsius. Careful. Careful. 0 degrees Celsius. And what's standard pressure? 1 atmosphere. Remember, you're at the beach at sea level. 1 atmosphere above your head. Okay. All right, so let's see. It says how many milliliters at STP are there in 15.26 grams of oxygen gas? All right, so 15.26 grams of oxygen gas. So you just have to remember, what is oxygen gas? Do you guys remember all of that? All of those diatomic gases? Hold on, do you guys remember this? Brinkelhoff. This is a list of all of your diatomic molecules, okay? They exist in pairs. You got bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. So we have oxygen gas. It's on there, okay? So you're not going to just say O. Oxygen gases, O2, because we're talking about oxygen molecules, okay? All right, so this is grams, and they want you to get all the way to molecules. All right, so let's just kind of review how this picture works. Technically, right now, you are on grams of your oxygen gas. Grams of your oxygen gas is over far left-hand side. So in order to get to molecules, you're going to have to go to this thing called representative particles. And you're like, what's that? Your particle could be atoms if we're talking about oxygen atoms. Are we talking about oxygen atoms, though, in this question? No, they're talking about oxygen molecules. I could have asked you to go to oxygen atoms in this problem, but did I? No. That would be that very last step between representative particles and parts of a particle. All right, so beware. We've done that before, going all the way to atoms, but we didn't this time. We're just going to stop at the molecule. So we're going to go from mass to moles using molar mass, and then we're going to go from moles to the representative particles using Avogadro's number. Oh, does it say milliliters? My bad. We're going to go to milliliters. Thank you. So we'll go from mass to moles, and then we're going to go from moles to volume using the, what is it, the volume, what do I call that? Molar volume of a gas at STP, which is 22.4 liters. So if they want you to go to milliliters, you're going to have to do a quick metric conversion at the end. Let's make sure you guys do that right. All right, so let's go. All right, here we go. Plan of attack. Know your plan of attack. So let's get rid of those grams. All right, so you got 2 oxygens. Each one is 16. Just double that. That is 32.0. I like to keep that 10th place in there, grams. And that is the molar mass of 1 mole of oxygen. Okay, so the grams are gone. Follow your unit. Remember the one rule, cross-cancel your units. So now you're on moles, and thank you for correcting me. We need to go to volume. So this is what we know. We know that 22.4 liters is equivalent to 1 mole of gas as long as that gas is at STP, and it is. All right, so knowing this information, all we're going to do is we're going to cross-cancel the moles. So you have moles on the top. You have to have moles on the bottom to get rid of it. How many moles, guys? Look at that. How many moles? Look. 1 mole. All right, so there we go, 1 mole. And what is that equivalent to? 22.4 liters. So we cross-cancel that mole. All right. Now we have this last step where we have to go from liters to milliliters. And you guys are killing me still. I'm still seeing mistakes on this. Can we just get this right, please? Liters. You don't see a prefix in front of that L, do you? Like K, H. You don't see any of these letters in front of it, do you? So that means that that L is on your base unit. You need to go here. From here to there. There are 1, 2, 3 jumps in between those guys. All right, if you want to move your decimal just to make sure that you're doing the darn conversion correct, move the decimal in the same direction that you are moving through the King Henry died by drinking chocolate milk thing, your favorite. Okay, your favorite thing. I hate King Henry. He died. Let him go. So please do this right. If you're trying to set up your conversion, let's just remember that I gave you some rules. The larger unit, which one's larger, liters or milliliters? Which one's bigger? Liters. The larger unit gets a value of 1. Now you did 3 jumps. Each of these jumps represents a power of 10. So what is 10 times 10 times 10? 1,000. The smaller unit always gets the bigger value. Okay? All right, so using that information, let's please fill in this conversion factor correctly. You need to get rid of liters. How many liters? Look at that. How many liters? 1. What is that equivalent to? 1,000 milliliters. So cross that off. All right, so anything sitting on the top is a multiply. Anything on the bottom is a divide. So I'm going to start with the 15.26 on my calculator. Hit divide 32. Hit times 22.4. And then hit times 1,000. I ignore ones because ones really don't matter. All right, answer here is 10682. This is what the calculator says. So now let's just have a short discussion about your sig figs. All right, so starting with the very first value that they gave you. This guy has 4 digits. This guy has, ooh, that 0 at the end, that does count. That's 3. 22.4 also has 3, and this is a metric conversion. What did I say about metric conversions? They do not count for sig figs. So should we have 4 or 3? 3. Always the lesser. Start counting your sig figs on the left-hand side. 1, 2, 3. Do you need to round your 6? Yes. So this becomes 107. Now what do I do? Because you don't want to chop that value off. What should I do? You can actually add 2 zeros if you'd like. That's perfectly fine because zeros at the end will only count if you see them after a decimal. You guys remember that? So this is actually 3 sig figs. The zeros at the end are not counting because I don't see them appearing after a decimal. Or, if you prefer, you just use scientific notation. To the 4, and remember this is milliliters. Either of these answers are perfectly fine. They're the same number of sig figs. All right, any questions on that one? That was a good one. Okay, now we're on number 10. So how many atoms of oxygen are there in 3.59 grams of nitrogen dioxide? And I didn't say this, but you can assume that this is at STP. If it does not say, you can pretty much assume it, okay? All right, so we want to go all the way to atoms of oxygen, key, atoms of oxygen, from nitrogen dioxide. Nitrogen dioxide is going to be a molecule. Do you guys remember that? Covalently bonded and all that stuff? Because, you know, you got like prefix, and these are both nonmetals. So you're starting with 3.59 grams of a molecule, and you are expected to go to atoms this time. So now, if you want to look at this thing down here, you will definitely need to go all the way to the far right-hand side in order to hit atoms, because nitrogen dioxide is a molecule, which is a representative particle. In order to hit atoms, you're going to have to do that last step. It's been a while since we've done that, so let's hit it. Number 10. Here we go. Starting with... how much? Can't remember. 3.59 grams. Okay, nitrogen dioxide. So there's no prefix on the nitrogen, so you can assume that that is just a 1. Di, what's that prefix mean? 2. Nitrogen dioxide. By the way, that's laughing gas. Ha ha ha. No? Okay, whatever. All right, and this is grams. So we're going to be doing some serious converting. Let's get down to it. So if you're starting on mass, what do you think I'm going to convert that mass into? Moles, you got it. So nitrogen has a molar mass of 14. Each oxygen is 16. You got 2 of them. I get a molar mass of 46.0 grams. Where should I place the grams? On the bottom, that's right, because you need to get rid of them. So I'm going to put the 46, technically 0.0 grams on the bottom, and that's equivalent to 1 mole of RNO2. Okay, so grams cross-canceled. What's the next step? What's the next step? Come down here and check. We just went from mass to moles. Where am I headed? All the way to the far right-hand side. So what's the next part that I have to do here? Avogadro's number. Do you see how Avogadro's number is in there? All right, well, how do we work that? You just need to remember that 1 mole of anything contains 6.02 times 10 to the 23rd things. And what thing is nitrogen dioxide? What is it? It's a molecule, right? Covalently bonded molecule. So we can label this as that's how many molecules there will be in 1 mole of this stuff, of nitrogen dioxide. All right, so let's cross-cancel. Follow your unit. You've got 1 mole. Obviously, I have to have moles down here. Look at that. How many moles? 1. And that's going to be equal to a ton of molecules. Okay, so we got rid of our mole. All right, use that diagram. Where are we? Well, we're on molecules, right? Molecules are a representative particle. But the question didn't want us to stop on molecules. It wanted us to get all the way to oxygen atoms. So now we have to do this little part right here where it says number of parts equal to 1 particle. And you're like, God, I don't remember how to do that. I know, I get it. Look at this. If I have 1 molecule of nitrogen dioxide, how many oxygen atoms would be in that? 2 oxygen atoms. Do you guys remember that we can use ratios like this as a conversion factor? For every 1 molecule of nitrogen dioxide, you will have 2 oxygen atoms. Use this entire piece right here as a conversion factor. So, what do we need to cross-cancel? Look back at the original problem. You need to cross-cancel molecules. How many molecules? Look at the ratio. How many molecules? 1. 1 molecule of nitrogen dioxide has 2 oxygen atoms in it. All right, so now do you guys remember all of that? Whew. All right, if it's on the top, you multiply. If it's on the bottom, you divide. I'm going to take 3.59 divided by 46 times 6.02 E23. I assume by now you remember how to punch in scientific notation. Please make sure you're doing that right. And then times 2. Ignore all the ones. All right, on the calculator, I get this. 9.39643, and it keeps going, times 10 to the 22nd. All right, so sig fig discussion again. 3, 3, 3, and this is a perfect ratio. That does not count. There's exactly 2 oxygen atoms in exactly 1 mole. So it does not count. So we should probably reduce this to 3. 1, 2, 3. Do you need to round that 9? Oh no, 9's round to 10s. So that's going to actually adjust this dude's value, huh? All right, so that'll turn into 9.4. Do I want to just stop there? No, you're going to want to include the 0 on there, okay? Because that's 3 sig figs. Times 10 to the 22nd. And what did we just get? Atoms. That's right. So we're going to say oxygen atoms. All right, guys, we're going to pause here. We just did problems 1 through 10. There will be another vodcast later. All right, this should get you started, though. Good luck, guys.